Okay, hey guys, good evening and welcome to week 3 of our CCNA Security MOOC. This week we're going to be looking at our topic of firewalls, and mainly with respect to how we enable firewall technologies in an iOS platform. We're going to look at a couple of pretty good lab examples that, again, packet tracer labs, just for ease of use. So I'll pop them up onto, I think I may have already popped them up onto Moodle. I'll check that out whether I have or not after the lecture. And you can download those and have a go at them yourself, but I'll be stepping through them here tonight just so you get an idea of how it all works. So first, we're going to do a little bit of a firewall primer in a Cisco sense. We're going to have a look at NAT, so some of the theory of NAT. It's relatively basic, and we'll go through a little bit of CLI stuff, but not a whole lot. There's not a whole lot you really need to understand about NAT in terms of the exam. It is one of the exam objectives, the official CCNA security exam I'm talking about here, not the MOOC exam. It is an official component of it, but it's fairly rudimentary, and you'll see through the CLI examples I give later on in the lecture that it's not too difficult to get your head around that. The main part of it is just understanding the different types of NAT and how they interrelate and how they're different from each other. So a bit of a contrast and compare. And then lastly, we'll have a look at some lab examples. Now, just in terms of questions tonight, guys, we had a lot of questions last week, which was absolutely fantastic, and I don't want you to not ask questions because I think that's a very important part of the learning, obviously. But I would like you to there'll be a couple of key spots that I'll stop and ask them and ask whether you have any questions. So just cue them up then, and I'll answer as many as I can. So there's usually a lot of overlap, so I'm sure we'll get through it okay. Okay, so firewall technologies. So firewalls, and this is just a brief overview of firewalls, and this is the same sort of stuff that you'll see in the CCNA security exam. So there's some general knowledge on your firewalling, and then there's some more specific iOS and Cisco-based questions that you'll be expected to know. So firewalls can be implemented as a single device, as a group of devices, say for example in a high availability cluster, or in software. Okay, so in that case we're talking about software packages that perform firewalling on your servers or your workstations. Now, of course, in terms of single or group of devices, they can be an appliance-based device. So say something like a Sophos UTM or a Symantec device, or even the Radware stuff. But they can also be like a dedicated server with software installed on top, like Checkpoint, although Checkpoint's more sort of in the appliance range and virtual server now. They can also, of course, be on a virtual platform as well, such as VMware running on a Cisco UCS platform. So there's a number of different ways. So when I say a single device, it's not necessarily a hardware device, it could be a virtual device as well. So the basic job of a firewall is to simply deny unwanted traffic. Okay, that's basically what it's about in the simplest form. This can be performed with a router with an ACL, as we saw last week doing some ACL examples. That's basic firewalling, okay, and that's historically where firewalling basically came from. The fact that we have these interconnections into our networks, and we don't want all traffic to go everywhere, so we use an ACL to separate that off. So that in itself is a rudimentary firewall. Of course, firewalls now have evolved a huge degree, and there's many other things that they can do, and we'll see that shortly. Another example is a switch with two separate VLANs. So if you have a switch with VLAN 1 and VLAN 2, for example, on it, and you don't have access to a layer 3 device, a router or a firewall or something similar, then traffic cannot pass between those two VLANs. Okay, in a typical ordinary configuration, they're not able to pass backwards and forwards between the VLANs. So that in itself is a rudimentary firewall, because the definition is to deny unwanted traffic. So it prevents unwanted traffic traversing between the VLANs. It's performing some sort of a firewall function. And then lastly, another example is a host firewall. So Windows firewalling or some other type of firewalling that actually on your software device. So firewall objectives. So the objectives of a good firewall. They need to be resistant to attacks. Okay, so if you've got a firewall and it's not resistant to attacks, then it's not particularly useful. As you can imagine, excuse me, I'm just coughing and spluttering a bit here tonight. Oh. Okay, just bear with me for a sec. I'm just getting my notes queued. Oh, go away. Okay, so anyway, as I was saying, so it's got to be resistant to attacks. If it doesn't resist attacks, as I said, then it's absolutely useless. So if it can fall victim to, say, a denial to the point where it can't provide normal access for your users, then, you know, it's a waste of time. The traffic between networks must transit the firewall. Okay, so if you've got multiple paths existing between, say, network A and network B, and a firewall is controlling the traffic for these connections, but then on top of that you've got an alternate path that goes around your firewall, then obviously any malicious traffic or nefarious traffic can go that way and bypass your firewall. So if your firewall's there but there's an alternate way around it and that's taken, then again your firewall's pretty useless. Okay, so it also needs to enforce your access control policy of your organisation. Okay, and what this basically means is, let's not put the cart before the horse. So if you think of it, many times the cart is put before the horse, okay, because as we put in new firewalls, rules are made for that firewall surrounding traffic that goes through the firewall, and then as a result of that, we then create our policy based on, you know, the rules that we've already put in. What we should be doing is saying, okay, let's not worry about the firewall for a moment. Let's document, let's think about what traffic we want to go through the firewall, what traffic we want to be denied, what traffic we need to do application scanning on, what traffic needs to be diverted to a DMZ, so on and so forth. Work out those rules about what you want the firewall to actually achieve, and then go and build your firewall rule base on that. Too often we build the firewall rule base first on the fly, because that's the exciting thing to do as techos. We get in there and we stick in our rules and away we go and we start blocking traffic and everything's great. But it must, you know, it must be in line with what the security access control policy of your organisation is. If it's not, then you've really got no way to, you know, you may enforce certain rules, but then you've really got nothing to fall back on from an administrative point of view, if that makes sense. Okay, so you should always have a defined organisational policy behind your actual firewall rule base, and that's to, you know, protect you from all sorts of different issues. Okay, so why do we have one? Why would we even bother having a firewall in the first place? The first thing is to restrict the exposure of sensitive information to untrusted parties, or trusted parties in some contexts, but not necessarily information that can make them. So by hiding most of the functionality of your hosts or network devices and permitting only the minimum required connectivity to those systems behind the firewall reduces exposure to that system. And so an example is, say...
Your audio is breaking up, Matt.
Okay, hopefully that's a bit better. See how that goes. Okay. So an example, as I was saying, is only allowing web traffic to a specific IP address of a web server in a DMZ, for example.
There's still a fair bit of static, sorry.
Okay. Okay, so I understand that we're having a bit of trouble with the audio, so I'm not sure how we're going to go. Just bear with me for a second, guys. I'll just put myself on mute, make a couple of changes, I'll be back very shortly. Hang on a second. Okay, let's see how we go. I think, as I've said in previous weeks, I've been having some pretty ordinary problems with my internet service, and tonight we've had a fair bit of rain, so it always seems to play up in the rain, so there might not be much I can do about it, but we will soldier on irrespective. Okay, if there's too many problems, I might just record the session offline and pop it up, but Please do let me know if it's getting worse. I'll just keep going on for a minute though. Okay, so getting back. Okay, so second point, exploitation of protocol vulnerabilities. So you can configure your firewalls to inspect certain protocols to make sure that they're compliant with the standards for that protocol across multiple layers in the OSI model. Okay, so you can also control the amount of time it will allow for a normal connection sequence before dropping a certain connection. Okay, so an example of this might be only allowing a specific amount of time between a DNS request and a DNS reply. Another good example is a three-way handshake for TCP, and the firewall only allowing so much time for that TCP three-way handshake to complete between the client on one side of the firewall and the server being accessed on the other side of the firewall. If it goes on too long, just cut the connection dead. Okay, unauthorized users. So another one. By using methods of authentication, your firewall can control which users traffic is allowed through the firewall and be configured to block on all other traffic based on certain policies. So, for example, a firewall could leverage your AAA services using its local configuration or some other authentication server inside your network. For malicious data, so a firewall can detect and block a number of different types of malicious data which would stop traffic from reaching the intended destination. Of course, this function can also be provided by your IPS or IDS technology, which we're going to have a look at next week. So limitations. It's all well and good to say, let's use our firewalls, and we're going to use them and it's going to stop and protect us against these different things, but there's always going to be limitations. One of the main ones obviously is configuration errors. So the firewall's job is to implement security policy. So depending on what specific firewall you're using, what software or hardware platform you're using, there are specific ways of implementing features such as ACLs, which we looked at this week. There's packet inspection, network address translation, authentication, so on and so forth. If the firewall rules are not implemented correctly, or it may not even do the job that you're intending it to do. So it takes good technical equipment and good technical configuration for the policy to be implemented successfully. So you've got to make sure that you have the skills to be able to deliver the necessary technology to protect you in the way that you think you should be protected. Firewalls will break some applications. That's a fact of life, unfortunately. So not all network applications were written to survive going through a firewall. There's still a lot of legacy stuff out there that people use in a lot of different industries, and things just simply break going through a firewall. Not all the software developers haven't caught up with the big technology vendors and Cisco and Checkpoint and whoever else that have all these fancy application inspection platforms and unified threat management, as I call it now. A lot of applications just won't work through them. So you've got to be mindful of that. And sometimes in some places where they'll write custom applications internally, sometimes they just won't go through the firewall at all. So it facilitates creative thinking. Now, what do I mean by that? What I mean is that if you force people to go through a firewall, they may try to come up with some sort of creative way to circumvent it. Okay, so options such as forbidden instant messaging file transfers, okay, inside of another protocol, so that it might look like HTTP or HTTPS is one thing they may try. Okay, so in other words, tunneling stuff through, and that can be done with a variety of protocols. So a firewall that is capable of application layer inspection may be able to identify and prevent this type of tunneling, but it may not do. Okay, so and there's other ways that you can get around, using your firewall. As I said, it facilitates that creative thinking. Added latency. Okay, so if a firewall's given a huge job and it's given a massive job, okay, it's got to analyze all the traffic that goes through it. Now, if you're in a big production environment with a bucket load of traffic coming through it, it can take a few milliseconds or more per packet for the analysis, depending on what sort of the way you're treating your overall traffic. And that can sometimes result in a slight delay, adding to the overall network delivery traffic time. Okay, different methodologies. Let's have a look. We have 5 basic what we call firewall methodologies, and this is again, this is a key concept you need to understand for the Cisco CCNA security exam. We all know that not all firewalls cost the same amount of money. Okay, so some are cheaper than others. One reason because of that is capacity. Obviously, the more sessions, packets, and resources a firewall can deal with, the more expensive it usually is. But various firewalls also contain different features and have different methods for the way that they implement their services. So, as an example, we have static packet filtering. Okay, so that's one methodology. And that's basically your ACLs that we spoke about last week. There's a proxy server, which is also known as an application layer gateway, so ALG. There's stateful packet filtering. There's application inspection. And lastly, there's transparent firewalling. Now, transparent firewalling is probably more to do with placement of the actual firewall device than it is of a specific technology in comparison to the other technologies here. But it's still a valid methodology. So if we look at each one of these in a little bit of detail. So static packet filtering, we basically covered that in depth last week, and as I said before, we already assume that you have a CCNA level networking background, so we would expect that you would understand an ACL and how that works. So we're not going to talk about that one this evening. ALG. So what is ALG? So it's, as I said before, it's basically a proxy server, or ALG stands for application layer gateways. So they operate generally at layer 3 and higher in the OSI reference model. So most of the proxy servers include some sort of specialized application software that'll take a request from a client, hence the proxy, puts that client on hold for a minute, and then turns around and makes a request as if it was its own request out to the final destination. Now obviously proxies can work from an inside-out methodology, but also outside-in. So basically the proxy firewall acts as an intermediary between the original client and the server. There's never any direct communication between the client and the destination, and because the application layer gateway can operate all the way up to layer 7 in the OSI model, it has the potential to be really, really granular and analytical about every packet that the client and server exchange, and therefore can enforce rules based on anything the firewall sees. Okay. Now I'm not talking about specific products here, just talking about in general. So the advantages are you get very tight control. They can be difficult to attack because of the fact that they span the whole OSI model. They have very detailed logging, and they can be implemented on commonly used hardware. So often you don't need anything super special to be able to implement them. It can be implemented fairly easily. Cons, of course, there's CPU, RAM, and hard disk drive heavy. And that the reason for that is reasonably obvious, and that's simply because they have to search all the way up to layer 7, up to the last layer in the packet. So it's got to strip off all that encapsulation that happens from layer 1 to layer 7 and read the content of the packet as it goes up and down based on its rule set. So it can be quite heavy on resources. Application support, so not all applications are supported. Okay. And in reality, they may only support a very specific few applications. And the other one is often you will need some sort of special client software may be required. Okay, so they can be, but they've got some. If you're looking for tight control, difficult to attack, detailed logging, well, then it might be the way to go for you. Okay, next one. So stateful packet filtering. So stateful packet filtering is pretty much one of the most important firewall technologies in use today. Okay, and it's called stateful because it remembers the state of sessions that are going through the firewall at any particular time. So suppose, for example, let's use an example. Suppose a non-computing one. Now let's say that you're with a mate and you go off to the go-karts or something, and halfway through the day you realise that you forgot something you left in your car. So on your way out to retrieve whatever it was, your wallet or something, say for instance, you wonder if you're going to have to pay to get back in again. The person at the gate explains that they'll give you a stamp on your hand, you know, elephant stamp or something, so that when you return you can just show that and you'll get back in for free. Okay, and then let's say, for a purpose of the example, that they also write our names on a list of people who are already on the inside and we're going outside to the parking lot with the purpose of coming back in. Okay, so when we want to come back inside, the people at the gate check the list and see that we've already been on the inside and that we left just for a short time, and they let us back in. Okay, so that's similar to the way your stateful packet filtering works. So if we continue that example with the stateful packet filtering, for customers on the inside of the corporate network, so your users, as they're trying to reach stuff on the outside, on the internet or other partners or DMZs or whatever, public connected networks, their packets have to go through the firewall on the way out, obviously. The firewall takes a look at the source IP, destination IP, the ports in use, and any other layer for information, and remember that information in what's known as your stateful database or your state table on the firewall. A bit like writing the names down on a bit of paper, giving you the elephant stamp. Okay, so it's called stateful because the firewall is remembering the state of the session that was on the way outside, including the ports and IP addresses involved, and that potentially something could come back in response to that. So normally the same firewall does not allow any traffic from the outside and untrusted networks back into the private network. But the exception to this is for return traffic that actually matches the expected return traffic based on that stateful database information in your firewall. Okay, so in summary, the reply traffic goes back to the user successfully, but attackers on the outside trying to initiate sessions are denied by default. So in other words, if you make an outbound connection, the return traffic for that outbound connection will be able to come back in, but if someone tries to initiate one from outside that doesn't already have a matching state entry in your state table, it doesn't get in. So the pros of our stateful packet filtering devices are that they can be used as a good primary, they are excellent primary defense. Okay, it's supported in iOS, so you can use it on routers and obviously also dedicated firewalls. It's dynamic in nature compared to static packet filtering, obviously, as per my explanation, and it'll also provide some denial of service protection and also against spoofing attacks as well. On the cons side, application layer or layer 7 attacks may not be identified correctly, or they may not be prevented. Not all protocols contain tightly controlled state information. So for example, UDP and ICMP aren't always nice and tight with their state information. So in that case, stateful packet inspection isn't as successful as what it may be with TCP applications. Now, some applications use dynamic ports. So in other words, they dynamically open up new ports from the server, and if a firewall is not analysing specific applications or prepared for this server to open up a new port, it could cause a failure of that application for the end user. If a firewall also supports application layer inspection, it might be able to predict and allow this inbound connection, but it may break it as well. And they don't support user authentication on their own. So this doesn't prevent a firewall that implements stateful packet filtering from also implementing authentication as an additional feature, but in and of itself, it doesn't support authentication. So there's other things that you need to install for that to happen and configure. Okay, next one is application inspection. So what we're talking about here, application inspection firewall can analyze and verify protocols all the way up to layer 7 of your OSI reference model. But it doesn't act as a proxy between the clients. So before we were talking about application layer gateways, okay, so it's a proxy. It'll go all the way up to layer 7 as well, but it will proxy on behalf of either the internal user or the external user. So, because remember, you can use your ALG, your proxy gateway can be used both ways. Okay, some products can be used both. Some products can only be used outbound or inbound. Others can be used both ways. A lot of the more complex ones nowadays are, just bidirectional. You set up your rules, whatever direction you want them, and it will work in either way. Whereas with the application inspection here, what we're talking about now is it'll inspect all the way up to layer 7, but it doesn't act as that proxy, so it doesn't do anything on behalf of anyone else. It just looks at the traffic going by, views it, and away it goes. And it'll do whatever it needs to do based on your policy. So extra pros, so it's very similar to your stateful packet inspection, but it's got extras in there as well. So extra pros, it can view deep inside the packets. Okay, so in this case, if an application needs to negotiate dynamic ports, and the server initiates one of the dynamic ports back out to the client, the application inspection, if it's been analysing that conversation, it'll dynamically allow that connection from the server to allow it through the firewall and out to the client. Okay, so this would allow the application to work all the way through unrestricted. There is an awareness of layer 7. So if there's a protocol anomaly which is a deviation from the standard, for the standard, whatever that standard is for that actual protocol, the application layer firewall could identify this and either correct the packet, so actually manipulate it so it conforms to the standard, or denies it altogether. And lastly, it'll protect against more attacks than stateful on its own. So firewalls, the current firewalls today, so for example the ASA, or the zone-based firewall solutions that Cisco offer, have the ability of packet filtering, stateful filtering, and application inspection all on a single device. Okay, so with those additional features, there's more types of traffic can be classified and then permitted or denied based on whatever policy you want. Okay, and then lastly, the transparent. And as I said, this is more to do with where the firewall sits rather than the actual technologies used to filter it. With a transparent firewall, we still have two interfaces or multiple interfaces, but we don't assign IP addresses to those interfaces. And those two interfaces act more like a bridge or a switch, if you want to talk about a switch, a two-port switch in the same VLAN. So traffic from one side is going to be forced through the transparent firewall if those packets have to reach the other side. Okay, so it's still routed, it's still pointed in that direction, but it's not specifically routed. It's almost like it's switched through. But you can still have your firewall policy which overrides the top of that and checks everything as it goes through. So, and the good thing about that is that users accessing resources through the firewall won't even be aware that it's even present. Okay, and that's one of the biggest advantages of using a transparent firewall. They don't even know that it's there. The other thing that's a really big advantage is you don't have to readdress your subnets if you're going to put a transparent firewall in line. Okay, you can have the same subnet on both sides of your transparent firewall and just pop it in the middle. And it's still, and because it's working basically at that layer 2 level, it's switching, it's working on the MAC address. And away it'll go, switching backwards and forwards across the transparent device. It still applies a policy, but it just sits there at a lower layer and you don't even know that it's there. Okay, so I'll just pause for the moment in terms of the presentation and I'll just have a look through the questions. So it looks like there's only a couple at the moment. So one about ALG to go both ways, or do you have to pick which way? I answered that one just before actually in what I was talking about. So yes, you can have ALGs that go both ways. Last one, more and more attacks from inside the corporate network. Should you firewall all from a corp user LAN to a server LAN? Potentially, yes. You might want to do that. Look, but again, as any good engineer knows, it is the answer to any question, engineering question, is it depends. It depends on what you're actually trying to achieve, what you're trying to protect, how valuable it is, what sort of information it is, how users access it, whether they do it remotely, whether they transfer files, whether they use specific applications that require certain ports that are open. So it all depends on what you're trying to achieve. So there's no there's no one that is better than the other. Okay, and I think we've got a couple of firewalls based on that. Yeah, look, there is no one firewall better than another. It's a horses for courses type thing. Depending on what your situation is, what your requirements are, then you need to change. You need to have a look and say, all right, well, a transparent firewall would fit there, an application layer gateway firewall would fit there, so on and so forth. Now, for example, UTM is all the rage at the moment, Unified Threat Management. So that includes all sorts of things. It does antivirus, it does email proxy, it does application layer gateways, it does stateful packet inspection, it does blah, 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 blah. It does lots of different things. But, you know, in reality, are many people going to use all the features of a UTM device? Probably not. There will be some people that will, but some people that, you know, it's not going to make any difference to. They may use one feature of it. So it may be better, say for instance, if you've got, for the rank and file small office, home office, or small business, or even small, what I would call small enterprise, you know, maybe 300 or 400 users, that sort of size, then you're looking at, you may not need, and they're just a standard, everyday sort of, they don't provide any, they have their web servers hosted externally, they accept a little bit of incoming email, they have some VPN users, and otherwise it's mainly outbound traffic, which fits the profile of most small to medium-sized organisations now. You don't need a UTM device or an application layer gateway. Now, you can get away with a stateful packet inspection type firewall, which 99% of them now are at that level anyway. You're not going to see too many that just do access lists. You may in the home office type situation, but again, most people aren't going to need anything other than that anyway. It all comes down to how valuable the information is that you have. If you don't have anything of particular value, or you don't provide an opportunity for hackers to be able to use your network to do something else, then chances are you're not a soft target. So if you're not a soft, cushy target, then they're not going to go for you in the first place. So the answer is, which one's better? Horses or courses. It just depends on what you're doing. Question, just another one. So I'll only do a few more because I'm mindful of time. I don't want to drag on like we did last week. If I don't answer your question specifically, please post it to the forum and I'll answer it there during the week. Okay, so main differences between ASA and firewalling technologies. Not a whole lot of difference. Mainly the way you manage it. On an ASA, you'd manage it through ASA, through ASDM, a Java application called ASDM. But there's also, you know, capacity issues. There's different types of hardware in the ASA, more interfaces, so on and so forth. And there's other inspection protocols that you're able to use in an ASA. You're also able to, well, you can terminate VPNs on a router as well. But it's just beefier. Okay, so the version on iOS is just a little simplified, a little stripped down, and we'll have a look more at that as we go into our lab. So I think that'll start to become a little clearer. Hardware firewalls. Okay, so examples of hardware firewalls. Cisco ASA is certainly one, although that's now in the process of going to virtual. There's the Juniper NetScreens, which have been fantastic hardware firewalls for quite a while. Checkpoint now do an appliance. Symantec do an appliance. There's a number of different vendors that do hardware platforms as well, and most of them, or quite a lot of them, will also do software or virtual versions of that as well. Do transparent firewalls add any more latency to traffic than the other types of firewalls? Not typically. Not typically, no. Again, because it comes down more to the layer in which you're looking at the information. So if you've got an application layer gateway, it's digging right into layer 7 on the packet. So it's going to take longer to whip through that than it would if it was only looking at, say, your layer 4 port information and source and destination address. Okay, so it's more to do with how deep you look into the packet. So from that point of view, transparent firewalls, any transparent firewall that does look that far into the packet is going to deliver similar latency hits as, compared to any other firewall. Okay, let's move on. Okay, so I think I've answered most of those. Okay, if there's anything different, there's one about CBACK and ZBF. We'll have a look at. We've actually got a CBACK lab, so that might be answered as we go further on. Okay, so network address translation. Just want to talk a little bit about that. So, important feature that's often implemented on firewalls, okay, because it converts IP addresses from private to public, and as we know, good design practices would normally dictate that you would have private IP addressing on the inside of your networks. Not always the case, but normally you would have that on your internal side. And network address, and therefore you need to translate those addresses on the outbound in order to get out to the public routable internet. So it first came about because we could see that there was a shortage of addresses. Okay, so we use our everyone, if we think ideal world, everyone uses their private IP addresses inside the network, and therefore we can have less public addresses out there that people need to use in NAT to. Realistically, obviously that doesn't happen, but so RFC 1918 private IPs, as I said, they are not public addresses. They must use NAT to route to the internet. So if you look up, if you're unsure what RFC 1918 addresses are, have a look at the, Google lookup for the IEEE standard RFC 1918 and have a look. Most of you will know what they are, even if you don't think you know what they are. So they're the 10 whatever addresses, any address starting with 10, any address starting with 192.168, or any address starting with 172.16, all the way up to 172.31. And so they translate between the private and public addresses. It hides a specific private IP. Okay, so it's been debated, and this is a debate that goes on in security, between all sorts of security professionals. Some argue, well, it's security by obscurity. Why would NAT is not a security feature? It's a networking feature, so on and so forth. And there's lots of different people in both camps. Okay, and it is a heated debate. Can get quite heated about whether it is or isn't a security technology. I'm not going to enter into the debate here, other than to say, I think, as part of a whole defence in-depth security policy or security architecture, you should look at any sort of technology that might give you a competitive edge over people that are trying to break into your network. So if NAT is part of that, great. If not, I'm not going to disagree with anyone. Okay, it's not required with IPv6 at the moment, but let's wait and see. I think in the future it will be. I can't see how it couldn't possibly. With the absolute explosion in all things connected, 99% of us have, 99% of the people I know have have multiple devices that can connect to the internet. I know IPv6 is a massive address space, but I'm not going to say never. That's for sure. So types of NAT. Okay, I just sent a comment. There are private IPv6 addressing spaces, ranges. Yes, there are. I'm talking about NAT. So I'm saying, what I'm saying overall, in theory, they say NAT is not necessary with IPv6 because there are so many addresses. That's all I'm saying. Sorry, I didn't make that clear enough. So, good point. There are private IPv6 address ranges, but with the amount of address space there, theory is you shouldn't need it. Okay, so types of NAT. Static NAT. So static NAT is a one-to-one translation between two addresses or between a port on one address to the same port on another address. Okay, so port 80 on one address to port 80 on another address. Okay, or a one-to-one translation. So it's a statically defined NAT. This address goes to this address. This address on the outside that we present on the outside goes to this address on the inside. Okay? So pretty straightforward. Your dynamic NAT uses a pool of global addresses to dynamically translate outbound traffic. And we'll have a look at these, each of these in more in depth in a minute. Okay, NAT overload with PAT. So it's slightly different again. So this is a feature that's been used for most, that is used for most users accessing the internet. So it takes the benefits of your dynamically assigned global addresses only when needed, and it uses overload so that literally thousands of devices on the inside can be translated to the same outbound global IP address. And as we said, and the router tracks all those ports and IP addresses in use to maintain the NAT translation tables. So the PAT global addresses include a single IP address that is already assigned to the outside interface of your router in this case, because we're talking about iOS devices. And then a single global address dedicated for the use of PAT. So it can be a, sorry, let me step back, whoop, rewind, let me get my thoughts in process. Okay, now fast forward. So the PAT global address can be a single IP address that's already assigned to the outside of your router. It can be a single IP address that's dedicated for the use of PAT, but not necessarily attached to the iOS router, or it can be a pool of global addresses allocated for the use of PAT. So you can either have an IP address connected to the router, an IP address assigned for that purpose but not directly connected to the router, or you can have a pool of global addresses. Okay, so you can have multiple addresses that you're going to use for your PAT on the way out. So terminology. Okay, this can get a little tricky for some people, and it's important that you understand what the differences are between there's four major types of classes, I guess, or descriptions of NAT addresses that you need to understand in order to be able to successfully negotiate anything, any questions or any labs involved with NAT. And they can get a little bit confusing. So let's have a look. First of all, there's inside local, the term inside local. That is the specific IP address that is assigned to an inside host, such as a computer. Okay, so it's real IP configured, it's real IP that is configured on the inside host. So that's the first one. That's pretty straightforward. So inside global is the address that identifies that same inside host on the outside of your network. So if you consider you've got your corporate LAN on the inside, you've got your internet outside, the inside global address is the address that identifies your inside PC or host to people on the outside. So it's basically the global address that the router is swapping out for the inside host during the NAT process. Okay, so the outside world will see your internal PC coming from this address, the inside global address. Okay, outside global. So this is the real IP configured on an outside host, such as the IP address on a server that you're trying to access. Okay, so it's just, again, it's just out there. It's a real IP address that's out there. So it's the IP address that everyone can access that server from. And lastly, there's outside local. So that's the address that identifies an outside host on the inside. So it identifies a host that's outside your network to devices that are inside your network. Okay, so if you're performing NAT on outside devices, so outside NAT, this is basically the mapped address of the outside device, such as www.cisco.com, as it would appear to your hosts on your internal network. Okay, if you're not doing outside NAT on your router, then this will just appear as a normal outside device's IP address to the inside devices. So it could, the outside global and outside local are sometimes one and the same. It depends on whether you're doing outside NAT or not. So as you can see, that gets a little bit muddy, a little bit confusing, but it's important that you really understand what those four terms mean. And I'll put up a couple of NAT resources on Moodle for you to have a look at. That will help you make that make those connections between those four. So the important thing is that these four terms are all about establishing a particular reference point. So the inside and outside have to do with where the IP exists, the actual IP address exists, before we make any NAT changes. Okay, it is either inside our network and under our control, or it's outside our network and therefore out of our control. So that's your inside and outside. Okay, if it's inside our network, it's under our control. If it's outside our network, it's not under our control. The local and global part then have to do with the appearance of the address and can therefore be pre or post your NAT. Okay, so the inside, so as an example, the inside local address will originates from somewhere under our control, and this is what the address looks like locally on our network before we do any NAT to it. But the same address after you've applied a NAT to it is called an inside global. Again, it originates into our network, but it's looking at it from an outside perspective. Okay, so look, I'll be the first one to admit Cisco have made this really confusing. It can be really confusing, but take your time with it. Have a look at some of the resources that I've put up and step through it. And then if you have any questions on it, post it back up onto the forum. Because I know from previous experience, I can sit here all night and discuss what inside local, inside global, and outside local are, and it's not going to make a lot of sense. To a lot of people, it is quite a complex set of terminology. So I'll just move on for a minute, and hopefully it'll make more sense as we go through. So just the example, okay, hopefully this might help as well. So we're looking at this example here. We're going to consider, so on the left-hand side we have host A, 10.1.1.10. And we want to consider traffic moving from host A on the left-hand side through the NAT router A and then through to host B. Which this router over here on the right-hand side is also labelled router A. That may seem confusing, but it's actually, what it's talking about is router A in reference to the host B organisation, router A in reference to the host A organisation. It took me a while to work that out. It is a little bit confusing, but it's a good diagram. Okay, so if we consider traffic moving from left to right in our diagram, the inside local on host A is 10.1.1.10. Okay, so that's the actual physical address that is connected to that particular host. The inside global address, remember, is the inside host as it appears to the outside world. So in this case, we're going to NAT 10.1.1.10 to the inside global of 55.1.1.1. So that's the inside global address. So that is how host A will appear to the outside world. On the other side of it, the outside, you'll see over here in the note here, if I just get my highlighting spotlight, static NAT translation 99.112 to 192.168.1.5. So there's a static translation on this router A, and yes, I know there's two router A's. Just take it that this one is in reference to this organisation, this one's in reference to this organisation. A little bit confusing, I understand. Okay, so we have that translation between those two IP addresses on this router. For the purpose of our terminology, the outside global for host B on the right-hand side is 99.1.1.2. Okay, so that's the way this host will appear to the outside world. The outside local is the same, and the reason it's the same is because of this key statement here is we are considering traffic from host A to host B. If we were considering traffic in the opposite direction, then this would change. But we're considering traffic from A to B, so the inside local is 10.1.1.10, inside global, how the inside host appears to the outside world, 55.1.1.1, The outside global of the host we're trying to get to, which is host B, is 99.1.1.2, and the outside local is also 99.1.1.2 because we're considering it from this perspective over here. Okay. Just had a question, shouldn't it be 99.1.1.1 instead of 99.1.1.2? No, because on the router on this side, if you have a look at this statement here, we've got a static NAT translation on this router which translates 99.1.1.2 to 192.168.1.5. So the outside global for this host, because we're considering traffic from host A to host B, should be 99.1.1.2. Okay, so I hope that makes sense. Because remembering we said before, our NAT can be an IP address that's on the router, it can be an IP address that is just allocated to a device, or it can be a pool of IP addresses. Okay. What if it was dynamic NAT? Well, if it was dynamic NAT, who knows what? We don't know what IP address it would be, but it's still the same. It's still the same process. Okay. It's more of, don't worry about the IP addresses so much. Just think about the terms inside local. So if we're considering traffic going from left to right in the diagram, inside local is the address of your host, your PC. Inside global is how your PC appears to the outside world. Okay, in this case it's a NAT-enabled router that's just overloading. Your outside global is the host that you're trying to get to across the internet, its global address that's available to everywhere. And the outside local, in this case, is still the same IP address, so 99.1.1.2, because it's an internet accessible host. If we were to go this way from right to left, then the inside local would now be 192.168.1.5. Okay, that's your inside local. Your inside global would be 99.1.1.1.2. Your outside global would now be 55.1.1.1, as would your outside local. Would be the same. Okay, so the vast majority of time, irrespective of which way you're going, the outside global and outside local addresses will be the same. Okay, the majority of the time. Not always the case, but the majority of the time. And for most examples you will see on the exam, that will be the case. The outside global and outside local will be the same. Okay, I agree, it is confusing. As I said, there's some good resources that I've posted up onto Moodle that I'll get you to look at, but I don't want to spend too much time answering questions about it just during the lecture, otherwise we'll be here all night because it is quite confusing. So let's move on. Just a quick look at some of the NAT configuration commands that you may or may not need to know. It's not, you won't be doing too much NAT configuration, but you will possibly be asked, you know, what does this command do? So you'd be expected to know that. So first of all, you need to identify your inside and your outside interfaces, and the way you do that is with the following command. So let's say, for this case, we're looking at a little a DSL router with a DSL or an ATM. Presumably a DSL interface. So int FA0/0, so that's your normal syntax to get into your interface mode. IP NAT inside, that's your command. Okay, so that now says that your fast Ethernet interface is the inside from the perspective of your NAT. Okay, and int ATM0/0 IP NAT outside. So that now says, okay, now for the purpose of my NATing process, the outside interface is considered to be my DSL. And that's the simple part. If you want to map public to private IP addresses, which of course you normally would, you would do it this way. IP NAT inside source, so we're saying IP, we obviously that's your protocol, NAT, this is a function, from the inside interface, so traffic initiated from the inside, with the source address of 172.16.1.1 will be statically mapped to the public IP address 203.193.205.50 in this case. So that sets up your static IP address translation. Okay, now it's source translation, so we're translating from the source, so the inside PC, for example, or inside device, going outbound. So when this PC, if my PC was on 172.16.1.1, that would be my inside local. When I went to initiate my connection outside to whatever web server I'm going to, my inside global would appear as 203.193.205.50 to the outside world. Okay, dynamic NAT configuration. Again, you need to identify the inside and outside interfaces. That's the same way as before. So int FA00, IP NAT inside, int ATM00, IP NAT outside. So it's still the same. You then need to create a pool of global addresses, and you do that using this command. So IP, again the protocol, NAT, this is what we want to do. The pool, so we're specifying a pool here. The pool name, so you can make that whatever you like, as long as it's descriptive and you understand what it is, that's cool. Then you put in a range of addresses. So in this case, 203.193.193.1 to 203.193.193.50 with a net mask of 255.255.255.0. Okay, so subnet mask /24. So the addresses that we'll allocate will be between 203.193.193.1 and .50. You then so that's to say these are the addresses that we're going to use for NATing. You then need to identify which addresses to NAT. So which addresses are you going to apply this pool to? And you use an ACL for that. So simple one, ACL access list 10 permit. So again, it's a standard ACL, okay? And this is a source, so we can only match by source. Because we're just identifying traffic, interesting traffic that we want to put in the pool, we only need a standard. So access list 10 permit 172.16.1.0 with the subnet mask, wildcard mask 000.255. And then you need to apply that ACL to the NAT pool. So IP NAT inside. So again, protocol function inside, so addresses from inside. Source translation. List 10 means basically take whatever traffic is matched by access list 10 and apply the IP addresses, the global IP addresses from the pool name, whatever you called it, use those to translate those private addresses on the way out. Okay, your NAT overload configuration. Again, identify your inside and outside, so we know how to do that. Identify which addresses to NAT using your ACLs. So again, access list 10, permit 172.16.1.0, wildcard mask /24. And then simply apply that ACL to whatever your overload interface is. So in this case, we're using the ATM00 interface. So IP, again, protocol, NAT, function, inside, direction, from where is the traffic coming. We're going to do source translation. We're going to match list 10 to anything in the 172.16.1 range will be matched. And we're going to send it out through interface ATM00 overload, which basically means just use the IP, the public IP address that is assigned to ATM00 as your NAT address. Okay, troubleshooting NAT, and you don't need to know these in too much detail, but I just want to make you aware of some of the commands that you can use. So useful basic commands, show IP NAT statistics. So that'll give you an idea of what's being matched, how many matches are made, and so again, just basic information. You debug IP NAT. Be careful with this because it can generate a lot of traffic. So it's a bit like we talked about last week or the week before, debug IP packet. Well, you know, if you don't use your ACLs, you can generate a lot of traffic. Show IP NAT translation. So that'll show you actually active translations on your router. So you'll see static, dynamic, whatever translations are happening on your router, you'll clear them. And the clear IP NAT translation is a command that will clear all those translation out, which can be useful sometimes if things get caught or hung up, or you change a static translation, for instance, and it's not working straight away. It could be because your NAT translation is still using the old static NAT one. Clear the translation table or reboot the router if you wanted to, and away to go. Okay. So before I get into the lab, I just want to talk about a bit on the design, and then we'll have a look at one of the labs. Okay. So design considerations, access rules, and no, not too bad. Okay, just let me cue my notes up here. I can. Oh, now I've lost them completely. Bear with me for a sec, guys. Apologies. Okay. So some of the things that you need to consider for the purpose of the exam. So, and this is not exhaustive list, but it's some of the key things that you'll need to know for the purposes of passing the CCNA security exam. So it's a partial list of best practices. In general, firewalls should be placed at security boundaries, okay, such as between two networks that have different levels of trust. And that's taking into perspective your organisation. So it could be even internally within your organisation. So say, for instance, you have your general rank and file users and your HR organisation. There may be a level of, there may be different levels of trust there. Okay, so in this case, the everyday users may be your outside perspective, and your HR department may be your inside perspective. So an example, so yeah, and the other obvious example is your internal network compared to the internet. Obviously, that's an obvious example. A firewall should be a primary security device, but not the only security device or security measure on the network. So again, defense in depth. Policies that start with a deny-all attitude and then specifically only permit traffic that is required are a better security posture than a default permit everything and then deny traffic that you don't specifically want. Okay, so the idea is you should really deny everything first and then specifically permit in rather than take the opposite approach. And a bit in answer to what we were talking about a couple of questions before, you need to leverage a firewall feature that best suits your needs. For example, if you know you've got thousands of users who need to access the internet, you can implement dynamic NAT or PAT for those users along with stateful filtering and denying all other inbound traffic coming from the internet. Okay, so this will stop the user on the internet from initializing sessions into your users because of the denial on the outside interface, but it allows the users to access the internet because you're performing your NAT dynamically for them. Return traffic coming back from the internet will also be allowed because the stateful filtering is being done and the firewall can dynamically allow the return traffic. And if you want to, say, allow only specific users to the internet, you can enable additional AAA authentication methods to allow that to happen. Okay, so again, you leverage what you need. It depends. The answer is always it depends. You need to make sure that physical security controls and management access to the firewall and the infrastructure that supports them are secure. Okay, so it's no point having a whiz-bang firewall if anyone can plug up to it and reconfigure it. You need to have a regularly structured review process to look at your firewall logs. So there's bucket loads of tools out there that allow you to do that, but you need to, whatever tools you need, whatever tools you use, you need to do that regularly to make sure that you understand what's going on with your firewall. And then lastly, the last one I want to talk about, and probably one of the most important, is to make sure that you practice change management, proper change management for any configuration modification on your firewalls. And if you don't do that, and you lose track of your account, you lose track of your changes, you know, a lot of trouble can come from that. So make sure that you place a real emphasis on making sure that your changes are fully tracked. Okay, access rules. So as I said just previously, the appropriate method for implementing firewall rules is based on a policy that you've already got. Okay, so the policy drives what the firewall configuration should look like, not the other way around. And there's bucket loads of different types of access rules which you can implement. And for example, some of them are, some of the ideas you could go through are rules based on, say, service control. Okay, so they're based on the types of services that might be accessed through your firewall, either inbound or outbound. So an example of that might be web services, HTTP, HTTPS. Okay, is allowed. You might allow that, but deny other types of traffic. You might base your rules on address control. So that's primarily on source and destination. Okay, nice simple way to do it. You might base it on direction. So basically they specify where the initial traffic can flow. For example, a rule might say that traffic from the inside going to the outside, outbound traffic, is permitted. Traffic initiated from the outside going to inside resources might be denied, for example. So just note that stateful filtering with the stateful database that it keeps could dynamically allow return traffic back to the inside users if so configured. And these types of rules, direction-based, can be very easily combined, and typically are, with various services such as HTTP, HTTPS, FTP, basic internet type services. You can have you can have rules based on user control. So these rules control the access based on knowing who the user is and what the user is authorized to do, which clearly needs to be implemented with respect to AAA as well. And then we also have rules based on behavior control. So the rules control how a particular service is used. For example, a firewall may implement an email filter to protect against spam mail, as an example. And then the last thing I want to talk about before I go into the lab, just quickly, is design guidelines. Okay, so regardless of which type of rules you choose to implement, there are some guidelines for the creation of those particular rules. So first one, which we spoke about just briefly before, use a restrictive approach first as opposed to a permissive approach for all interfaces and all your directions of traffic. By using this as your starting point, you can then permit only traffic that you want, while you can deny everything else. So it might take a while to fine-tune because you often overlook or discover additional required protocols and functionality as you go along, but it's worthwhile going to that effort because you'll get a much tighter, much more securely controlled firewall environment. You need to presume that your internal users' machines may be part of the security problem, because often they are. If you blindly just decide that everything inside is fine, you allow everything out, this can easily allow an attacker who has physical access to the building or malicious code that's been downloaded onto your desktops to be exploited. So don't assume that everything internal, that all your friends really are things. Be as specific as possible with your statements. So the typical one is don't put in any or all if you can absolutely avoid it. Okay? Absolutely avoid it. Try to be as specific as granular as you can. Recognize that there's a necessity of balance between functionality and security. Okay, with security, there's always this seesaw, as I like to say. Okay, there's always that how secure you want it. The more secure you make it, the less usable it is. The more usable you make it, the less secure it is. Okay, so you need to balance that up between functionality and security. Customers have a network for a reason, and they need to allow traffic through firewalls to allow their business to function. But at some point, you might need to point out specific weaknesses based on allowing something through your firewall, but allow the traffic anyway based on the business need. Okay, and it's usually up to someone higher up the chain than you to make those final decisions. But if you are making that decision, then just be aware that there's that balance. Filter your bogus traffic and perform logging on the traffic. So some packets should never be allowed into your network. For example, your own addresses should not be, or particularly if you're using private, but your own addresses should not be allowed into your network. So if you start seeing your own addresses, your internal addresses coming from the outside of your network, there's something wrong there. Okay, so block that type of traffic and log it. See where it's coming from. And lastly, but most importantly, periodically review your policies that are on the file to verify that they're current, they're working, and everything's good. Okay? If there's rules, it's one of the real pet hates I have is in a lot of places I've worked, firewall rules will be added in for a new function or a new server or a new something or other, but then the old ones aren't taken out. Okay, they're not taken out. That's really annoying. You need to keep your firewall base, because a firewall base that's cluttered with a lot of legacy rules is every bit as dangerous as a rule base that has any or alls in it. Okay, you need to make sure that the rules are there for a reason and they work. If they're not required, get rid of them. Simple as that. Okay, quickly, zone-based iOS firewalls. Features, they do stateful inspection, application inspection, packet filtering, URL filtering, transparent, support for VRFs, and no need for ACLs. Good God. A lot of things that they do. Okay, let's look at an example. Even better. Just sent a comment. According to Cisco, layered security is required. Not just according to Cisco. That's pretty much best practice, in any security vendor will tell you that you're better off having defense in depth and different layers of security rather than just one firewall or one set of security protocols. So if we look at this here, if we look at our diagram here just quickly, we have an inside zone where our inside PC users live. We have an outside zone, which is our internet servers, users on the internet. And we have a DMZ zone, okay, which is where our internet accessible company managed servers exist. So this is a pretty vanilla flavored type of zone-based firewall, and pretty standard sort of configuration. So we allow traffic from the internet in through our outside interface to the DMZ, but we don't allow it any further. So we don't allow outside traffic, outside initiated traffic back into our inside. We only allow it into the DMZ. From the inside zone, we allow all traffic outside, and we generally allow most traffic into the DMZ. From the DMZ, you may occasionally allow traffic that's specific traffic that's for very specific purposes from the DMZ into the inside zone, but generally you would only allow return traffic, because if you're allowing outside traffic into the DMZ and something gets compromised, then they can pop into your inside zone if you have inside rules coming from your DMZ. But again, it depends. It depends what you use. Okay. Configuration pieces for our zone-based firewalls. We need class maps, which identify our traffic. We have policy maps, which are actions that we're going to perform on our traffic that we've identified. And we have service policies, which basically are an application of that policy to a particular point in the configuration. As part of our policy actions, so in other words, our policy maps, we can do the following. We can inspect the traffic. We can pass the traffic through. We can drop the packet. Oh, look, I'm going a bit too fast there. Sorry, guys. We can drop the traffic altogether. So again, it depends on what you actually want to do with it. And lastly, you can log the traffic. So what does that basically all mean? Well, your inspect is basically permitting and statefully inspecting the traffic. Okay, so it's used on traffic initiated by users who expect to get replies from devices outside the firewall. Okay, pass simply allows the traffic but doesn't do any stateful inspection. Okay, it just lets it go through. Drop denies the packet altogether, so we don't care where it's going. It's dropped, done. And log the packet is basically if you want to see log information about the packets that were dropped because of policy, you can add the log option on, and it'll keep that information about why the packet was dropped with respect to the policy. Okay, so if we have a quick look at the service policies. So a service policy in a zone-based firewall is applied to the zone pair. And if we just whip back a bit to a previous slide here, you'll see the zone pair here is the out to DMZ. Okay, so we've paired up the outside and the DMZ zone, and we're going to create a policy out to DMZ, so outside through to your DMZ. So with respect to that, with your service, so that's what a zone pair is, okay? So your service policy is applied to a zone pair. So the zone pair represents a single direction or unidirectional flow of traffic between the two zones. Now, a specific zone pair, in this case outside the zone, can only have a single service policy assigned to it. Because the zone pair is unidirectional, the policy map applied to the zone pair applies to traffic initiated in one zone going to the other zone in one direction. So in this case, it's, in our example, it's an application of traffic going from outside through to the DMZ. If reply traffic is denied, the inspect action has to be applied, which will then allow that stateful inspection to occur, and of course if you're expecting a reply, then that reply traffic will load back in. So see how the different features interact. So when a router normally receives a packet, it will make a routing decision and then forward the packet on its way. If your zone-based firewalling is configured, the router may or may not forward the packet based on the stateful table and your policies that are in place. Okay, and this particular table here tells you how that, what will actually happen, the actions that will happen. So if your ingress interface is a member of the zone, so in this case your ingress interface, so it's coming from the outside to in, so your outside interface, the ingress interface. If it's and then you've got your egress interface, so the interface going the other way. If neither of them are a member of a zone, then the zone pair and policy, doesn't matter whether it exists or not, the traffic will just be forwarded. Because basically we're saying don't apply any security to these interfaces, let's just forward the traffic. If we have the internal interface, the ingress interface is not a member of a zone and the egress interface is, irrespective of any zone, then again it's irrelevant which way the traffic is, whether the pair and the policy exist. The traffic in this case will be dropped, and this is because one of the interfaces is a member of a zone. Okay, so it's a high level of security. So it's like, no, okay, we're going to drop it. All right. If they are members of a zone and they're the same zone, okay, so they're both DMZ or they're both internal or they're both whatever, then it doesn't matter what the policy is, it will be forwarded because they're at the same security level. We're all happy. Everyone's happy. If your ingress interface is zone 1 and your egress is zone 2 and there's no pair or policy, then traffic's just dropped. If your ingress interface is zone 1 and your egress interface is zone 2 and there is a policy, the zones are paired and the policy exists, then what happens to the traffic will depend on what policy is in place. Okay? So spend a bit of time getting your head around that table. It's actually is relatively straightforward, but take a little bit of time just to get through it and make sure the penny drops, because that's important. It's a good summary of ZBF and worthwhile getting your head around. Okay, let's have a look very quickly at some labs, because I'm mindful that we're going a bit long tonight as well. Let's have a look at what we've got. So these will, again, I will post these up onto Moodle for you to have a look at, so our online learning portal for you to have a look at. And this is a diagram that we're going to look at. Now, have I got my, let's see, yep, that's still up nice and big. Excellent. Right, okay, so this is a diagram we're going to be looking at. Let's make it a little bit bigger. Second set. So we're looking at a zone-based policy file, as you can see up here, configuring a zone-based policy firewall. So what we're going to do, we're going to create some rules on here. And so we're going to create a couple of zones. So we're creating an in-zone and an out-zone. We're going to pair them together, and we're going to put some rules onto the particular zone. Okay. So we need to, first of all, make sure that we can get where we need to get. So if we just jump onto our PCA, our server, and we're going to the desktop, we're going to have a look at our command prompt. We need to make sure that we can get to PCC over here, which is a 192.168.3.3. So let's ping. See if we can get that far. Wait for ARP to keep going, and there we go. So we've got connection all the way through. So we're right there. Now, from PCC, the other thing we want to test, if we go to PCC, desktop, oh, there's one. Wow, what do I keep pressing on that? we'll put the IP address on that there. It's a bit silly, isn't it? So we want to telnet, I want to try and telnet to router 2. I can tell you that the IP address of router 2. Now again, you'll see this when you actually load the lab yourself, but I just want to transmit, I want to go through the lab step by step so you get an idea how to do it and what it looks like, the commands we're going to be using. So you won't necessarily see all the detail in the demonstration, but once you actually see the lab, it'll make a lot more sense. Okay, so we can telnet to the router, which is cool, so we don't need to prove anything else there. So we've got access, what we're basically saying is we've got access from here through to here, and we can ping from server A back to PCC. Now, another thing we want to do is open a web browser. 2.168.1.3. Okay, there we go. So now we've got access through our web browser through here. So now what we're going to do is we're going to, so we can see now that we've got connection from PCC through to PCA, web browser, we can ping back, we've got telnet access to router 2. So what we're going to do is we're going to configure a zone-based policy firewall on router 3. Okay, we're going to pop some rules on there that's going to restrict some of our traffic. So if I just grab my, where is my snippet? Just going to grab my configuration snippet here. Okay, so because of course I've already done this. So what we're going to do, the first step we need to take is, as we said we were talking about before, is we need to create a policy map to determine what to do with our matched traffic. Oh, hang on, what am I doing? I'm going step forward. Idiot. The first thing we've got to do, I'm getting ahead of myself here, is we need to create, so the first thing we need to create is our internal zone, okay? So we need to use our zone security command. So if we open up router 3 and we go to our CLI, and we've got Cisco 5 done, and we enable Cisco, oops, PA5. Okay, so we're at a command line interface on router 3. Go to configuration mode. So the first thing we need to do is create our internal zone. So to do that, we would go zone security in zone. Okay, so then that opens up the security zone configuration. We're then going to create an external zone as well. Now we can do it directly from here without having to go exit out. Well, we should be able to. Security out zone. Just exit out of there. Then we need to create. No, we'll do that later. Okay. So now we need to work out what traffic it is that we're actually going to permit, or what traffic we're going to identify that needs to be placed through the zone-based firewall. So, and how do we do that, folks? How do we do that? How do we decide what we're going to match? Just making sure you're all still out there. Anyone? How do we configure that? What would we use to decide what we're going to classify as interesting? Access list, there we go. There we have the winner. Okay, access list, correct. So in this case, we're going to create our access list. I'm just going to cheat here, cut and paste it out of my document. So we're creating an extended access list, and we're permitting 192.168.3.0 with wildcard MAR 000.255. So that's anything from the 192.168.3 network, okay, to any source. Done. Now, does anyone? And so then the second part of that then is to then create. We need to create a class map which references that ACL. And the way we do that is thus. And I'll just, because I've already done it before, I'll cut and paste it just so I can get through it. So we use our class map type inspect. Okay, so it's a stateful packet inspection class map. We're matching all and we're going to call it in-net class map. And we're going to match access group 101. Now the match all, okay, the match all keyword, that can be either match all or match any. If you say match all statements that you put inside this class map must match before it's registered as a hit. Okay, if you put in match any, then any one statement can create a hit. Okay, so it doesn't maybe seem too much of a big deal, but it can be a massive deal. So just bear in mind it can be match all, match any, and depending on what the requirements are of the question, you may need a match all or a match any. Okay, so it might say something like, if any one of these traffic types is met, it creates a match, or it may say all of these conditions must be met, and that's the difference between using a match all and a match any. Okay, so we now create a class map, we've created an ACL, we've created a class map, and we've got our zone, we've got our zones created. However, the next step, oh no, we'll do the, no, we'll do that next. Okay. All right, so the next part would be to specify your firewall policies. So in this case, we're going to use a policy map to do that. So let's, again, I'll do my copy and paste. So policy map type inspect into out. Policy map. Okay, so we're mapping traffic inwards on the outbound direction. The class type inspect in-net class map. So you can see how this now, the policy map here, is now tied to the class map that we just created by using this statement here. So the policy map will then be applied, well, you'll see where it's applied in a minute. The policy map is then applied to a specific interface or a specific zone or a specific set of rules. And the class map needs to be referenced, so we reference our class map by using this command. We tie it to the policy map, and then the class map in turn is tied to an access list which determines what our interesting traffic is. And in this case, it's an inspect policy map. Now, it's just said there, no specific protocol configured in net class map. That's right, we didn't because we've just matched on an access group. So it's saying now all protocols that will come through via this method will be inspected. Okay, that's fine. We don't mind about that at all. Okay, now we need to apply this somehow. Okay, we need to apply that somehow. We'll do that using, and we're pairing, we will now pair our zones together. So we've got an inside zone and we've got an outside zone, but we haven't paired them together. Remember that concept of pairing them together? So we need to do that. We do that by zone pair security into out Z pair. So again, inside to outside, zone pair. Source is the in zone, destination is the out zone. Okay, great. Now we tie our service policy to the zone pair in this case. Okay, so service policy, so we've just configured that before. Service policy applies to the zone pair. The class map is applied to the service policy. The access list is tied to the class map. Okay, so see how it all flows up. You have access list going to class map, going to policy map, being applied to your zone pair. Okay, so it's almost exactly like, well, it's similar, very similar concept to the way we apply quals. Okay. And then, lastly, the last thing we need to do is to actually, now that we've got the zone pair and we've got the policy map applied and the access list and all that, everything applied, the last thing we actually have to do is apply that to the relevant interfaces. So now at the moment, we've got these zones created and this access list created and this policy map and class maps created, and they're sitting there in memory, but they're actually not doing anything because we haven't physically applied them to anything. So the way we do that is we go to int FA01 because that is this interface here pointing out towards the local network, and we need to apply that. And the way we apply that is thus, with a zone member, security in zone. So we're saying it's going to be a zone member and it's in the security zone in zone. Okay, so that's done that. Of course, that's the inside. That's great, but where's the outside? So it's a bit like NAT, inside, outside. Yeah. So we apply to our outside interface, which in this case, and you'll just trust me on this one, but that's just the interface. Again, you'll see it for yourself when you go through the lab, and I suggest you do because it'll help to reinforce it. And we paste. So again, zone member security. So it's a member of the security zone out zone. So now we've got our inside and our outside. Okay, so now if we go back to our server A. Sorry, no, we don't want to go to server. Wrong way. So if we go to our PC and we go command prompt and we ping to our server, which is 192.168.1.3. See, ping replies, all good. Now let's see if we can telnet, say, to router. So we want to telnet to our second router again, which from memory was 10.2.2.2. Okay. Actually, I can't remember what the password is on that one. Oh, there you go. Good guess. Excellent. Okay, so we've telnetted to our interface, to the telnet interface. So the telnet's going to succeed. So while it's active, what we need to do is, okay, no, I'll just leave that. Doesn't matter about the password. If we go back to our router 3 now, that's not router 3, you idiot. So if we go to router 3, here we go, yep. And we have a look at, if we have a look at the policy map, what's actually going on, type inspect zone pair session. You'll see here that we've got our zone pair in zone, out zone, our service policy that it's applied to, our class map that applies to that, our access group, we've got inspection enabled. You can see an established session from 192.168.3.3 coming from ephemeral port 1027, and it's going to 10.2.2.2 on port 23, which, as we know, as we should know, is the port for telephone. So we can see it's an open connection created 51 seconds ago, last heard from 21 seconds ago, so on and so forth. Okay, so if we refresh that command, you can see the counts will increase as we go. You can see that then tells you that the zone base is working. Okay, so if we look at some of these, the source IP, there's your source IP and port, there's your destination and IP port then. Okay. Alright, so if we just go back to our PC for a second and we exit out of our telnet session and we go to our web browser, and this time we go to 192.168.1.3, and if we go back to our router 3, and we do that again, okay. Oh, there we go. We must have got something wrong. Because that should be, isn't it? That should be showing up a session from our PC to our server. But we're not getting anything out of it. It's gone completely dead. Let's go again. Don't you love demonstrations? Not a cracker. I'm not sure what's going on there because that should definitely be showing up. So we're not getting it all. There you go. What do I say? Never work with kids or animals or packet tracer labs. Because sometimes they don't give you the results that you're expecting. But yes, anyway, it's made a bit of a liar, but what it should show is a similar thing to what we saw before with the telnet session, but in this case actually showing the HTTP session going outbound, because we're going from here across router 3 out to here. We haven't specified any protocol, so all protocols should actually match, so that actually should be showing something up there. So I'm not quite sure what's going on with that, but nevertheless we shall continue on with our testing. So now if I was to go back to here and I was to try and ping that host from there, from the server, you can see now that we're not getting any pings going through, and that's because we've created that zone-based firewall on router 3, and that ICMP traffic is being passed outside, being passed from the outside in, and it's not going to allow it because it's not expecting it. It doesn't want it. So that, in a nutshell, is a zone-based firewall. Okay, and again, I'll pop the lab up on Moodle, and you can have a bit of a look at that and give that a go. There is another lab I want to quickly go through because I think it'll be worthwhile for you. So let me just shut down this lab. Bear with me for a second. Now we don't save that, because if I do that, that will change what I put up for you guys. Of course, the other option there is that I completely messed up my cut and paste. I'm not sure how I would have done that, but anyway, that's always a problem. Best laid plans often go astray. So let's have a look at our CBACK lab. Let's see if I can get through this one without any cut and paste errors. Of course, I'm just assuming I made a cut and paste error. Let's wait and see. Okay, so in this example, again, I won't bother going through the particular verification steps. Oh yes, we will. All right. We'll go through the verification steps. So ping 192.168.3.3. Let's see if we can get through this one. So waiting for ARP, and there we go. So we've got our connection all the way through. You can see that already. We'll use our telnet. Oh, sorry. Channel. Whole technology in my head. Okay, so we can see we can access our telnet command as well from there. The other thing we want to do is run our web browser. Make sure we can get through to there. There we go. Goody gumdrops. Everything's working as we would expect it to be. So number one, in our, so what are our, let me get my configuration. Whoop. Let me get my configuration up. So again, this particular configuration will be applied to router 3 because we're taking the perspective of PCC, of the PC going outbound to the server. First thing we want to do is we need to create an extended IP access list. Okay, and what we're going to do is pretty much drop everything. Oh, I'll get password right. Hello. T. Just make it a little bit bigger so it's a bit easier for you guys to see. See the old mate configuration line. Okay, so we're going to create our access list, deny anything, and we're going to apply that to the serial 001 interface because that is the serial interface that's connected to, in our network diagram, that's our interface here. It goes back out to the rest of the real world. Come up here, Mr. Router. Mr. Router. Okay, so int serial 0/0/1. You're going to create IP access group, out, in. Okay, so what that effectively does is that denies all traffic. That denies all traffic on passing through from the outside. Passing through. So if we were to go to here, and again we were to ping, so if we ping our server, bingo, there you go, you can see we're not getting anything out. Okay, so which is what you would expect. With an IP access list that says deny any. So now what we want to do though is we want to create a inspection rule or a CBACK rule that's going to inspect ICMP, Telnet and HTTP traffic. Okay, so we want to inspect all three of those traffic types. The way we do that is thus. So IP inspect name in out in. I know lab's a little bit confusing, but I'm following along with the lab. So for ICMP, Telnet, and HTTP. The other thing we want to do is to turn on audit trail. So IP inspect audit trail. So basically what this does is it turns on the CBACK audit messages so that you get a record of the network access through the firewall, including anything that's illegitimate as well. The other part of the lab talks about setting up some logging, so I'll do that as well. We'll log to the internal host 192.168.1.3. Okay, so we turn our logging on, and then we're going to apply this particular configuration to, because we always have to apply it. It's great that we've got it in there, but we haven't applied it anywhere, and we're going to apply it to the serial interface in the outbound direction. So IP inspect, out in the outbound direction. Okay, so now let's test our PC. So we'll just make that window a little smaller so you can see that there. We'll jump into our PC and we'll just get our router. Bear with me for a sec. I'll just rearrange my windows so you can see everything. There we go. Good. We're going to try and ping our server again. And now you can see not only does it work, but it's also been logged, audit trail. Okay. So now we've got our pings back, but it's been actually looked at. Now if I try to telnet, telnet to our 10.2.22, again, oh, I think I've totally hosed up that password. I have. Okay, so again you can see the session now starts and it's logged. Okay, so we can see it. And then last of all, let's try our web browser, 192, enter 1.3, and again start the HTTP session. So it creates that. It's not only is it allowing that traffic out now, these firewalls are allowing out, but it's also inspecting it and logging that as well. Okay, just looking at what else do I want to talk about in this lab. Okay, if we have a quick look. So if we have a look at our session, and let's just add a bit. So you can see that so it shows you session, sequence, the session number, and then the IP address, source, port, source, destination, IP address, and port. Okay, so if we were to just go in there. Okay, so it's only going to show that one for me. Okay, and you see the session is now stopped, so if we go back to here, we've got nothing. Let's try our ping session. Okay, there we've got our ICMP present, so you can see there's the source IP and the ICMP code, so code 8. So it's an echo request, and then the destination and ICMP code 0, which is echo reply. Okay, so cool, love it. If we have a look at some of the other options, so IP inspect, so say we look at statistics, it gives you an example of some of the information that's available. Okay, so maximum session counts, established 2 sessions, okay, so we've done a couple of sessions, created since last system subset for the last up. And so there's a little bit of information there about the actual the sessions that you can use. Let's have a look at, if we have a look at config, there's another interesting one. Okay, so it'll show that your ordering is enabled, session alert is enabled, TCP wait time, your different TCP counters, and then your inspection rule configuration. Okay, so your name and what it's inspecting. Okay, ICMP alert is on audit trail, is on timeout of 10, so on and so forth. So it'll tell you what it's actually looking for and what it's actually going to alert on. Oh. So last one, what else do we want to look at? We can have a look at interfaces. And again, this just simply shows you where your inspection rules are set and how it's set. So that's, that's probably one of, to get a quick snippet of what's going on in your router, that's, nice, easy, quick configuration to have a look at. You could also, of course, go show run and have a look at it through there. It's a little more disjointed, typically, with the run because, you've got your IP inspect commands up here. And as you scroll down, you've got your configuration that's tied to your actual serial interface. And then as you scroll down further, you've got your IP access list. Okay, so it's a little bit more disjointed. If you just go to the config, the interface, not config, interfaces, it'll give you pretty much everything you can get from your show run. It's just not in the same syntax. But it gives you an actual, gives you an idea of what's going on straight away. Okay, so that, guys, is, I believe, hang on, I better go back to my presentation, so I might say it is. Okay, it is. That's all I want to talk about tonight. So, again, a little bit of a long one, but I think it's worthwhile to go through the labs at the end there just to make sure that you've got something to go on with. There's plenty of articles that I've put up over the last week with respect to that, and with respect to, there's quite a bit of firewall stuff up there, so have a look at those, read through those, and check on, make reference to what was spoken about tonight. The PDF version of the slides are already there. You would have seen those the other day. Hopefully, if you've already jumped on, had a quick flick through them. I'll also put up the packet tracer labs if I haven't. I think I might have already, but I'll have them anyway. And also the video will be available on YouTube. Now, I understand, I see from the comments there's been a little bit of problems with the audio tonight. I'm not sure what's going on there, so hopefully my recording will be fine. I'll get that put across, and the guys at IT Masters will be able to pop that up onto YouTube for us, and that'll also be available through the online learning portal. So next week we're going to look at IDS technologies, and again it's specifically how they apply to iOS devices. Otherwise it's the same time, same place. Once we get past next week, we'll then be looking at VPN and a little bit of encryption in the last week, and then the week after that the test will be open for you to do. However, I'm planning on doing a webinar on the Monday night anyway, just to talk not about the MOOC exam, but to talk a little bit about the actual the Cisco security exam itself, so, and give you some information on the sorts of areas you need to focus on and some tips for taking the exam. So obviously we're not going to go through any specific questions, so don't go thinking that will be, but we'll be able to we'll be able to have a chat about the sorts of topics that are heavily related on it. And most of that information is available from Cisco's website anyway, with respect to the weighting, but there's some other tips that I can give you. So that'll be on the Monday night of week 6, the week that your MOOC exam opens. So until next week, study hard, have a look at the readings. If you've got any questions that come out of tonight, and I'm sure you will because I'm sure I will have missed some, please pop them up on the forum for everyone's benefit, and I'll answer them over the next few days. All right, until next week, enjoy yourself, and I'll talk to you later. Bye.